Kia ora and welcome to the final video in the series Agile Algebra. Thank you to all of you who have been watching so far and have stuck with us through the various problems that we've been looking at. Today's question involves the binomial expansion, a binomial theorem, and the coefficients of such an expansion. It's going to be presented by a current student of mine. His name is Anatol. So he's going to go through the question. He's done a phenomenal job of the video. And shout out to all of the students of mine who have presented through this series and also the previous series. The caliber of the videos has been really high, and is relative to my solutions has definitely been impressive. So here is the question that Anatol is going to go through with us. So see, we've got an expansion. I guess a popular thing for people writing questions, maths questions, to do is to put the year, the current year in there. So there's 2023s in there. We need to find a general expression for the coefficients of that expansion. See that they range from A0, A1, A2, all the way to A2023. And then also find the value of the largest coefficient in the expansion. You can give this a go on Wolfram Alpha. It will definitely do the expansion for you. But good luck dealing with the size of the coefficient. But anyways, enjoy this presentation. It's brilliant, as I said, and it definitely explains how to do this problem really well. Pause the video, give it a go first, and I hope you've enjoyed this series. Ka kite.
Hey everyone, I'm Anatol. I am currently doing Schol Calc at Mags. Today, I'm going to be doing this problem Mr. Walden gave me. So we have this equation, x plus 2 raised to the 2023rd power, which equals this ugly mess on the right, which is a whole lot of terms. First of all, we need to find an equation for the coefficient an in terms of n, which we can think of as the coefficient for the x to the power of n term in the expansion. Then, we need to find the largest such coefficient. So let's jump into it. To do this, let's start by looking at a simpler example. Take x plus 2 raised to the 4th power. If we expand this, we'll get this expression here, and we can see the values of the coefficients we want. For example, a0 is 16, a1 is 32, and so on and so forth. However, we can get a clearer idea of where these numbers come from if we rewrite this expression like so, and then multiply the whole thing out. To get one term, we can start by multiplying all of the x's together. We write this as 2 to the 0 times x to the 4 because we are multiplying 0 2's and 4 x's together. Similarly, to get the next term, we multiply all the x's together except in the last x plus 2 part where we use the 2. We get 2 to the 1 times x to the 3 because we are multiplying 1, 2 and 3 x's together. Then, we just repeat this process with every combination of x's and 2's to get the full expansion. Now, as an example, let's figure out how we can get the a2 coefficient from this. In this case, it is equal to 24, as we can see from the 24x squared in the top simplified expansion. As you can see, there are 6x squared parts in the full expansion, which are contributing to the 24x squared. Let's take a look at the first one. As you can see, to get the x squared part of this coefficient, we are multiplying exactly 2 x's together, which gives us the x squared part, and as a result, we also multiply 2 2's together, which gives us the 2 squared part in front of it. We also get a similar thing for the next x squared coefficient, and the next one, and for all of them. Since there are 6 x squared terms, each with a 2 squared in front of them, we can multiply that by 6 and get a value for a2. Now, to get a general form, we just need to figure out how we get the 6. Why are the 6 x squared terms? Since each x squared requires us to multiply exactly 2 x's together to create it, The number of x squared coefficients is just the number of ways we can pick two different x's. To pick the first x, there are obviously exactly 4 options. Then, to pick the second x, there will only be 3 options left, since we can't pick the one we just chose. Then, we can just multiply 3 and 4 together. However, with this formulation, you may notice that we are countering different orderings of the same 2 x's separately, whereas we shouldn't do that. To stop this, we just divide our result by the number of orderings possible. In this case, since we are just picking 2 items, it is 2 factorial. Then, in each term, since we are picking a total of 4 x's and 2's, and we are picking exactly 2 x's, we must be picking 4 minus 2, or 2 2's. So, we can multiply our current result by 2 to the power of 2 to get the correct value for A2. We can also do a similar thing, for example, for calculating A3. Now, make sure you just understand how this whole thing works up to here. Now, we can write a general form for A of n, like so. However, this isn't a great general form, as we still have this whole ugly series of multiplications at the end, which you use to get the right amount of combinations. So, how do we write this properly? We can write it like this. I won't go into too much detail as to how this works, but we can get a good idea by looking at our A2 case from before. In that case, the whole string of multiplications boiled down to 4 times 3, which, using the equation I showed, we can write like this. Now, if we expand the factorials, we get this. We can see that the bottom factorial cancels out some of the top one and leaves us with exactly what we want. And so, now, we have a proper general form for our simpler case. Now, we can test this equation and see if we get a correct value for all of A, which we do. Now, the equation we just got only works for the smaller problem of x plus 2 to the power of 4. Remember, in the real problem, we have x plus 2 to the power of 2023. However, we can just fiddle around with what we had in the previous section and notice that we can easily get an equation for 2023. We just need to replace every occurrence of 4 with 2023. This is the answer to the first part of the question. Now, let's move on to the second part of the question. Remember that we are trying to find the largest coefficient in the binomial expansion of x plus 2 to the power of 2023. We will do this using the equation we just derived for the nth coefficient of this expansion. Now, since you are trying to maximize this formula, you may be tempted to try find its derivative. However, there are a few issues with doing this. First of all, our function is only defined for integer values of n, which means that the derivative isn't properly defined. Second of all, even if we do extend the domain of our function to all real numbers, the result would be a mess and include complicated maths like the gamma function. So, we will need another way to find the maximum of this function. Instead, we will look at the ratio of 2 consecutive terms in the sequence a of n. We can use this in a similar way as we would a derivative. For example, for a certain n, if the ratio is greater than 1, then the next term must be greater than the current term. If the ratio is less than 1, then the next term is less than the current term. This function also has the advantage that later on, when we evaluate it, a lot of things will cancel out. First, let's plug in our equation for a of n into this equation for the ratio. Then we can do a little rearranging of the n plus 1 parts. This allows us to split the top power of 2 parts, like so. From this, we can cancel out the power of 2 parts, and we're left with only 2 to the negative 1, which we can just write as 1/2. We are dividing a fraction by a fraction, so we can rewrite this as multiplying the top fraction and the reciprocal of the bottom fraction. This allows us to cancel out the 2023 factorial terms. With factorials, there is this very useful identity which can be easily derived from the definition of a factorial. We can use it to rewrite the n plus 1 factorial and the 2023 minus n factorial like so. Now we can cancel out a lot of things as they appear on both the top and the bottom of our fraction. And now we have a very simple equation for the ratio of two consecutive coefficients in the binomial expansion of x plus 2 to the power of 2023. Now, let's take a look at when this ratio is greater than 1, which, as you may remember from before, means that the terms are increasing at that point. Now, we can rearrange this a little bit and get an inequality for n. This tells us that up until n equals 673, all the terms are increasing, and the last increase is from the 673rd to 674th term. This means that the 674th term is the maximum term in the expansion. We still need to find the value of this term, which we can do by plugging 674 back into our equation for the coefficients. This is the final answer to the problem. You will not be expected to write out the actual digits of this number, as it is very large,